Hello. Okay, so now that we know about brushless motors and what's going on inside these wires here, it's time to take a little bit more of a look at the ESC, the electronic speed control that's managing all this current switching that's going on in here. And they're a pretty complicated thing, really, so I'm not going to be able to explain all of this in all of the detail that it involves, but we will at least be able to look at the basics and figure out what these wires are all doing and what sort of current is going on in this side of the ESC. And we'll also maybe take a look at how you can change the settings on these, because they can actually be changed. They're not a fixed program. I thought I might start off by explaining why it is that we even call these electronic speed controls in the first place. I mean, if they control the speed, why don't we just call them speed controller? Why do we have to call them electronic speed controllers? Well, back in the day, before we had all these cool little powerful electric motors, radio-controlled planes and cars and things were powered by petrol motors or gasoline motors, internal combustion engines, and they have a throttle that needs to be moved physically. It needs to be mechanically pushed backwards and forwards. So the way that was done was by using a servo like this, which has a physically moving servo arm, and that would be connected to the throttle on the motor, for example, like this. So that's the servo, and it's using this rod to push the throttle on the petrol engine. And here's one on a car as well. Where is it? There. So this is doing the same kind of thing. And normally you would, of course, have your servo connected to the radio control receiver, but I have it just connected to this thing here. This is called a servo tester. Lets me just manually position it to there, or I can make it go. Oops. Well, it can do this kind of full range of movement to let you check. For example, if you use this on a plane, you might want to check that it's not going to do something strange. Anyway, so that is a servo, and when we started getting nicer, smaller, lighter electric motors, we began to use this kind of a speed controller. So there's still a servo here, so this is the servo arm on the back, or the top side, and it's connected now to this little piece here, which is a variable resistor. So as the servo arm moves, it's going to change the resistance of this little piece, or it's going to change how much current can get through from the battery to the motor. So it's still a physical connection, and we have a mechanical movement going on in the car. But as electronics got a little bit more advanced, we were able to do away with all these old fossils, and now everything is contained in just a little circuit boardy thing that's much smaller and lighter. And the circuit boardy thing, of course, has no moving parts. It's all just an electronic circuit, and that's why we call these an electronic speed control. Now, in order to make the transition from gasoline engines to electric motors as easy as possible, they use the same method of communication between the receiver, or the servo tester in this case, to the motor. So I have my servo here, but I could just as easily swap this out with an electronic speed controller. And if I get this around the right way, we'll find that I can also whoops, need to. Now I can use the same control method to control electronically this motor as I was controlling physically this thing over here. So the method of communication that's going on in these wires is another form of pulse width modulation, or PWM, but it's a little bit different to the PWM that we looked at in the last video, so we'll have a look at that in detail soon. Let's take a look at a few different examples of ESCs and what they have on them, so that in the future, instead of just calling these a circuit boardy thing, we can maybe sound a little bit more educated, like we know what we're talking about. And if we have a look on here, the most important thing on these, or the core of everything, is this chip here, which is the CPU. It's like a little computer, and this is organizing all the high-speed calculations for what needs to be done. And over here we have a large, or relatively large, wire. Red will be positive, I hope, in most cases, and the black will be negative, and these are power wires, so they need to be a little bit larger, because these are handling all of the current coming in from the battery. So these two larger wires here will be connected directly to battery power, whatever that happens to be, 12 volts or 16 volts or something like that. And the other two wires, which are smaller, these are for communication. So remember, we need two of these. So the black one is going to be our ground reference to make sure that the other circuit boardy thing, the flight controller, is talking to us on the same ground reference. And then the white wire is going to carry the actual signal. So this white wire is going to be going up and down between 0 volts and 5 volts, or ground and 5 volts. It's going to be switching off and on, off and on. And it's the flight controller is going to be switching it, and the ESC is going to be listening for that voltage going up and down on this white wire. And the up and down is, like I mentioned just before, it's a type of PWM that we'll have a look at in a minute. But that's how the communication is happening. Over on this side, we have a few other things. We have a little voltage regulator. This little black thing there under my thumbnail is a voltage regulator. So these chips, these brains, they typically run at 5 volts. As we just said, the signal coming in is at 5 volts logic level. So in order to have a 5 volt power supply for this chip to run, coming in from the 12 volt supply or 16 volt supply from the battery, we need to have a little voltage regulator to step that voltage down from battery level to 5 volts. So that's what this one is doing. Next we have these 6 thingamajigs on here, and these are actually a type of transistor. They're called MOSFETs, which stands for metal oxide semiconductor, I think, field effect transistor. So it's a big long name, and people typically refer to these as FETs. So just the field effect transistor part. So if you hear people talking about FETs, this is what they're talking about. And to figure out why we have 6 of these, let's look at the circuit diagram of what's going on this circuit. This is, of course, a vastly simplified circuit diagram. It's not just this. But so those transistors that we just saw, we have 6 of them. And if you remember from one of the previous videos, a transistor is kind of like a switch. It allows a low power circuit to switch on and off a high power, high current circuit. So that's why it's got SW, short for switch. And they're arranged in such a way that we'll have 3 of them on the high side. So this is the battery here, and there's no labels, but you could imagine up here this is our positive battery voltage. So say 12 volts is up here, and then ground is down here. So 3 transistors will be on the high side, 3 transistors are on the low side, and they're all sort of connected like this in the middle. If you remember from my homemade brushless motor design, all the 3 coils were connected in the middle on one side of each coil. So that's what's going on here. And at any given time, one of the high side FETs will be turned on, and one of the low side FETs will be turned on. So that will let the current flow through in a specific path. For example, suppose that the leftmost high side FET, this one here, this switch was on, the other 2 were off, and on the low side, the one in the middle, let's say this was switched on, and these ones on the left and right were switched off. And when a switch is switched off, it's almost like there's no circuit there at all. It doesn't exist. So we could simplify this particular circuit diagram by drawing it like that. So we only have those 2 switches on, and that's the only place that the current can flow. And in that situation, the current would come down through this switch. It would go in to the U labeled coil, and it would come out through the V labeled coil. So that would make one of these magnets, electromagnets, a north, and one of them would be a south. I'm not sure which is which, but the point is one of them would be north, one of them would be south. And then in the next phase of switching, whichever way we want to switch it, we can make them switch around the opposite direction and so on. So that's why we see 6 FETs on these ESCs. It's not always 6, because you can put these in parallel to allow them to handle more current, and I think this one here actually. So on here we have 2 sets of 6 on this one. So I'm pretty sure that you'll find these in multiples of 6 in most cases. And one other thing I wanted to look at was the fact that we have a capacitor on here, and the capacitor is connected between the battery negative and positive. And if you remember from one of the previous videos, a capacitor is a small storage of charge that can be, it'll charge itself up and discharge itself as necessary. And I'm not entirely sure how this works, but if I understand it correctly, when these transistors are switching off and on, the electricity is flowing along the wire, and it's a bit like the water in a hose. If you've ever had a garden hose and you pinch the hose so that it stops, you'll feel it sort of jam up a little bit, just briefly, until the pressure equalizes. But I think something like that happens in that the voltage can be disturbed, and in order to make sure that the little brain here can run everything properly, it's safer to keep a little bit of charge available here to cover those rough patches and the disturbances in voltage that we could otherwise see if we didn't have it. I probably didn't explain that too well, but I don't understand it myself that greatly either. But suffice to say, we often find a capacitor over the negative and positive terminals of the ESC, and if we just look at some of these other ones quickly, they're pretty much the same. We just saw this one a moment ago. It's the same, pretty much the same, except it has 12 FETs instead of 6, but all the rest of it looks quite similar. And this one actually has some labeling. So this is a 30 amp rated ESC, and that means that it can, I think in most cases it means that this is the continuous current that it can handle. So you could run this continuously at 30 amps, which is pretty impressive for these little FETs. They do get hot. They can get hot in some cases. Probably with 12 of them there, this would actually be handling the 30 amps quite well. The 20 to 500 Hertz refers to the timing of the PWM signal that's going to be going through this wire, or the white wire there. So PWM, pulse width modulation, the pulses are going to be turning off and on at a certain speed, and this particular ESC can handle that switching off and on from a rate of 20 times per second all the way up to 500 times per second. Down here we have something called BL Heli, which we'll have a look at a little bit more in the later part of this video. But BL Heli is a little bit like the software. It's not really software and it's not really hardware. It's we call it firmware, and it's what's running on the little brain there. So we can actually change that as it happens. But BL Heli is the name of that firmware. And then down here we have LiPo 2 to 6S. Most of these ESCs you'll find they don't run on less than 2 cells LiPo, so they'll be starting from 2, and this one can handle up to 6S, or 6 cells in a row. A pretty big high voltage battery, 22 volts I think. So that's that one. We have this one here, kind of the same thing, 2 to 3 cells LiPo, so it's not rated to run at a 4-cell LiPo. You shouldn't use this one with a 4-cell LiPo. But we have again the brain there, and we have the capacitor there. There's something a little bit different to this one, which I'll come back to in a minute. So let's just quickly look at these other ones that are kind of the same. Again here we have BL Heli, so it's running the same firmware. This one is a 12 amp rated ESC. Opto, I think I'm just going to ignore Opto because they're a little bit, it's not actually a true Opto ESC anyway. But this one's rated to up to 4S. And this is the one that I'm going to be using on one of my builds in this video series. They're okay, but I probably wouldn't get these again today. There are much better alternatives for the price. And I'm a little bit skeptical about how well it handles 4S, because in my experience it flies pretty good on 3S, but if you start flying 4S quite aggressively, it just sort of seems to die after a while. Anyway, that's the brain on the back there. And then over here we have pretty much the same thing. Again, we'll see that this one is a 30 amp. It's rated 3 to 6S. It does run on 2S, so I don't know why they've put 3 as the lower. And it's also running BL Heli. At least when you buy it, it has BL Heli on it. You can probably change it to other things. And we don't have one of those big capacitors on this one, but we do have a bunch of smaller capacitors which do the same job. That's what these little brown boxes are on there. And the brain on this one is a different type of brain. It's a slightly different computer, so it's a bit smaller than the big one that we have on there, and it's a lot faster and much more capable as well. So this is sort of a bit more like the current generation of ESCs that are out there, and this one that I have that I'm going to use on one of my builds is pretty much last generation, or maybe even 2 generations ago. That is another reason why you probably wouldn't want this one today. Now, going back to this one, there was something a little bit different about this one, and not sure if you noticed or not, but this one actually has 3 wires coming out of it for the control connection. And there's a brown, which is this is the ground. Actually, it's usually black, but sometimes brown. In this case, it's brown. And then we have the yellow or the orange one at the top is the signal, which is quite often white, but in this case is yellow. And then in the middle we have red, which is a voltage wire. And if you remember when we looked at this first one here, we had where is it? So this little thing here is a voltage regulator, and it's taking the LiPo battery voltage from whatever it is down to 5 volts. And we saw one, I'm pretty sure I saw one just on here too. Yeah, there's quite a big one here. So this thing here is another one of those voltage regulators that steps the voltage down to 5 volts. And in this case, that 5 volts is only being used inside here for this ESC to run itself. But this one is also bringing that 5 volts out. So here's the voltage regulator on this one in the bottom left, and the 5 volts that this is giving the ESC to run itself is also being taken out here so that you can run something else. You can run, for example, your receiver or your flight controller or something else that needs 5 volts. You can get that by using this brown and red wire, so ground and 5 volts. So this red wire is actually an output for voltage. It's not an input going into the ESC. Let me just connect that up to my voltmeter and I'll show you what I mean. Okay, so I have my voltmeter ready now, and I'm running the ESC from a 3-cell LiPo. So that is giving me, if I put just use the balance connector to check the voltage across all of the cells, and that is 10.6. Ooh, that's getting a bit low. But if I test the voltage on here on the brown and red wires, we should see 5 volts or something very close to 5 volts on here. 4.993, that's not too bad. So the point is that for this ESC, it is actually providing 5 volts out through that wire, and that's what the BEC, battery eliminator circuit label there, is referring to. So for this particular ESC, you can actually use that 5 volts to power something like maybe your flight controller or your receiver or something that needs 5 volts. You can plug that in and power it up like that, which can be very handy. We tend not to see a BEC feature in quadcopter ESCs, especially recently these days. They're pretty much all of them made now are not including a BEC for a number of reasons. One is that quite often people are using a power distribution board or something like this that has a voltage regulator on it, so we don't need it. And we certainly don't need 4 of them. We do need 4 ESCs, of course, because we need 4 motors, but we don't need 4 voltage regulators because we only have 1 flight controller to run. Plus this type of voltage regulator is not very efficient. I can feel it getting quite warm now because what it's doing is taking that 10.6 volts and giving us 5 volts here, and the rest of the voltage is just being wasted as heat coming out of there. So there's quite a few reasons that we don't see a BEC on quadcopter ESCs anymore these days. Okay, let's have a look at the communication method that the ESC uses, or the flight controller uses, to talk to the ESCs. And this is another type of PWM, but it's a little bit different to the PWM we saw before. So I thought I'd take a look at this because it will explain some of the things that we see in the flight controller configuration software later on. So I have my oscilloscope connected up to the output of this servo tester. So it's just a voltage going up and down between 0 and 5 volts, again like we saw before. But if you remember from the PWM pulse that we saw before, last time it was switching on and off about 1,000 times per second, and when I had the dial, or yeah, I had a dial before, didn't I? Yeah. When I had my dial to 0, as it is now, we had just had a flat line. It was 0 the whole time. And when I turned my dial up to full, it would be at 5 volts the whole time. And when it was about halfway, it would be on half the time and then off half the time. But what we see here is quite different. For a start, it's not switching on and off so quickly. We only have about 50 times per second pulse. And it's off. And even though it's off, we have a pulse. It's not at flat at 0 this time. And when I turn it up to full, we'll see the width of the pulse does get wider. So it is doing some pulse width modulation, which is good, but it doesn't seem to be changing it all that much, does it? But we will be able to see what's going on if we zoom in a bit more on this pulse. So let me put it here. This is with my dial at 0, approximately 0. This is a little bit of a cheap one. It doesn't do things perfectly. Oh, actually, it might be supposed to do this, but you can see that's a little bit less than, so 1 square horizontally is 1 millisecond at this point. And it looks like it's a little bit less than 1 square, so it's a little bit less than 1 millisecond, and 1 millisecond is 1,000 microseconds. So if we were to measure the width of this pulse, I'd say it's about 950 microseconds, maybe 960, 970, something like that. So it's a little bit less than 1,000 microseconds. And if I turn it all the way up to full, it goes to about 2,100, maybe 2,200 microseconds is now the width of this pulse. So you can see that unlike the duty cycle PWM that we were looking at before, where the percentage or the range, the position that we are within the range, was conveyed by the percentage of time that the pulse was high, this is a little bit different. It's still PWM, but instead of using the percentage of time that the pulse is high, we are actually measuring the width of this pulse to get a range between, in this case, 1,000 or approximately 1,000 and 2,000 microseconds. So this is, I'm not sure what you call this one, but a servo communication PWM or something like that. Not only servos, of course, ESCs, as we're actually looking at ESCs, but they work the same way. So this is how this type of PWM is working. And you might be thinking to yourself, what is the point of this? Why can't we just use duty cycle PWM? Because after all, it's just one number. It's like how much throttle is on. Is it full throttle or is it halfway or whatever? So it's just one number, the same as it was for duty cycle. But the way this works is a lot safer, because on the receiving side, the ESC in this case, the ESC can check the width of this pulse and make sure that it is a sensible number. So we're expecting something from around 1,000 microseconds to around 2,000 microseconds. And if it's anything else, that means that something's gone wrong. And we might not want to spin the motor or something. We might want to just turn the motor off to keep it safe. For example, consider what happens if I disconnect this here. Yeah. Oops. Oh. Well, that'll do. So in this case, if we were just using a duty cycle PWM system, this is a perfectly valid input. It just means that the throttle should be at 0. In that case, it would be safe because the motor would stop and we wouldn't cut our fingers on the propeller or something. But if we were to touch that onto a 5-volt power source at some point, that would be, it would raise up to here, and it would think that the propeller should spin at full throttle, which could be very, very dangerous if we did not intend for it to be spinning at full throttle. So by having this type of a signal, we can check that the other end of the connection is alive and making sensible commands. The final thing I wanted to do in this video is to take a look at the firmware that's running on these ESCs, and this is just going to be a very quick look at it. We'll need to come back to this in much more detail later on, but for now I wanted to give you just a rough idea of what it is. And you may be familiar with the terms hardware and software. Hardware is, of course, the actual physical object that you hold in your hand, like this thing. And software you're probably familiar with from using a computer or an iPhone or an Android phone, where you start up the computer and then you can run all different kinds of software programs. So like you can run your web browser or your email, you can play games or whatever, and you can change those programs. You can put new ones on, and you can delete the programs all while the computer is running. And that's software because it's soft and it's easy to change. Firmware is not quite so easy to change, and the way it works is that when you turn this little computer on, it's going to run one program and one program only. That's all it knows how to do. So as soon as you connect up the battery, that program is going to start running, and that's all it does. You can change the program, but it's not as easy as software, and you can't change it while it's running. You need a special connection, which is what I have here, and you need special software to help you change the firmware, which is what we're going to look at now. So this is obviously an ESC. This is one of the BL Heli ones. So it's made to run the BL Heli firmware, and I have it powered up with a battery, and it is connected through this thing to my computer. So again, we'll come back to the actual ways you can do this. This is just one of many ways that you can actually connect to an ESC and modify it. But the point is, for now, that it is connected to the computer. So here's the computer that the ESC is connected to, and I'm running a program called BL Heli Suite, which lets you connect to an ESC running BL Heli and modify the settings, and you can actually even upload new versions of BL Heli. You can see there's the revision number shown there. I'm not actually connected at the moment. Let me just connect to that ESC and read the setup, and that worked okay. And you might have noticed that a few of these settings just disappeared because this particular ESC does not support all of those features that disappeared. But now we can see that it is running version 13.2. So anyway, there's a bunch of other things there that we'll look at, some of them in future, I think, maybe some of them at least. And yeah, just for now, I just wanted to give you a quick idea of what we're talking about when we say ESC firmware and BL Heli and BL Heli Suite and so on. So I think I'll leave it there for this video. There is of course a few more details that we'll need to look at when it comes to actually using an ESC ourselves, but for now I just wanted to give you a rough idea of how they work and get you familiar with some of the terms that people are going to be using when they talk about these things. So I hope that was informative, and thanks for watching. See you next time.